Hello, my name is Oliver Mays and I head the Research and Development Department here at ECOROLL AG. Today I'd like to provide some background information on deep rolling. So I don't want to go into deep rolling too much, but I simply want to show why we do it in the first place. Namely, because we extend the lifespan of components through deep rolling. And that's why today I want to explain the so-called SN curve in a bit more detail, which is a good way to provide fatigue strength and strength verification, and also to get a feel for how well my component holds up under a certain type of load and a certain load duration. The whole thing is part of the so-called fatigue strength verification. So when we design a component, design a machine, we actually always have to do a fatigue strength verification because we want the component or the machine to last as long as we designed it to. We've made certain assumptions for this, such as the type of load, how high the load is, and so on. We can design the component geometrically. We can select the material for it and things like that. That all plays a role. And with that, I can then go into the next phase of the fatigue strength verification and, for example, provide the fatigue strength verification. And the fatigue strength verification, the SN curve, plays a very central role here, combined with the corresponding safety factor that I then, set for myself, which my component should achieve. I can then carry out the lifespan estimation for my component. The SN curve itself goes back to August Wöhler. August Wöhler was a railway engineer who was born in Soltau, funnily enough, not that far from the current headquarters of ECOROLL, namely about 50 kilometers from here. And August Wöhler asked himself the question, why do our railway components actually always break even though they haven't even reached the static loads they were designed for? And he established a connection. He started a test setup in which he dynamically tested wheel set axles, and he found out that as the number of load cycles increases, the bearable load of my component decreases. We can see that today in the so-called SN curve. The SN curve is a diagram that plots the number of load cycles on the x-axis and the bearable load on the y-axis. And to simplify the representation a bit, the whole thing is often shown in a double logarithmic way, so that it then, so to speak, becomes a linear equation at this point and is easier to handle. And then basically a lot of tests are carried out and it's always plotted at which load and which number of load cycles my component breaks. And if I've carried out an infinite number of tests here and evaluate them statistically, then I get a curve that looks something like what I've sketched here. You can already see that it has three areas. One, I'll call it a static part, a falling part, and again a, static part at the end at low load. And to simplify the whole thing, it's often divided into, I'll call it three sections. These three sections can basically be, marked by straight lines. These three sections are referred to as the short-term strength range, or the low-cycle fatigue range. Then the range of time-limited fatigue strength. This is the range where, as Wöhler discovered, the achievable load decreases as the number of load cycles increases. This is the linear relationship here in the double logarithmic range. And then at the end, at the knee point, there is the range of so-called fatigue strength. Here we assume that if a component is loaded below the fatigue limit, this component will last indefinitely and will never break. And now this SN curve is actually relatively easy to read. All load combinations of cycle count and load that lie below the curve in the green area shown here do not break. All components that lie above it will break. It is actually that simple, and that is how easily this SN curve can be read. But now you have to pay attention to a few things, because the SN curve is a statistical evaluation. For example, we distinguish between the 50% and the 10% SN curve. I need to know that when I am talking about it. I cannot compare a 50% and a 10% curve. No, that just does not work. And it is always the result of a statistical evaluation of tests. Because no component will always break at the same cycle and load combination, there will always be a variance. And that is taken into account through statistical evaluation in the SN curve. What I also need to know about the SN curve is that it only applies to a single state. So it applies to one component, it applies to one manufacturing process. And this result of the SN curve also only applies to one type of loading. So I cannot compare a torsional alternating load with a tension compression alternating load and transfer one SN curve to the other. Similarly, I cannot transfer the SN curve from one component to a similar component. I can of course make assumptions that it is similar, but I cannot say this SN curve for component A applies exactly to component B. The nice thing is that I can compare SN curves with each other. If I take two different manufacturing processes, for example, I can compare them and say process 1 is better than process 2. That is a very nice relationship. And that shows just how simple this SN curve is as an evaluation method. To conclude, I would like to explain two effects that impact the SN curve. Of course, component diameter, notch geometry, materials, and so on, all affect the SN curve. But I want to focus on two that are very crucial for us here. And that is also the reason why I am providing this background information today. Specifically, the component roughness affects the SN curve, and the residual stresses also affect the SN curve. With component roughness, it's relatively simple. I have, through a higher or lower roughness, I basically have small micronotches. Small micronotches where cracks can form and which can then continue to expand and grow larger and larger under dynamic loading. And then, of course, I have a change in the SN curve. That means my SN curve shifts. If my component roughness increases, the fatigue limit is lowered, and my curve becomes steeper. Regarding residual stresses, which I can achieve through a deep rolling process, for example, so I can introduce compressive residual stresses through deep rolling. And these compressive residual stresses then also affect the SN curve. You can see here in the sketch that if I compare a turned component with a deep rolled one, the fatigue strength is set significantly higher. In the area of low cycle fatigue, we don't have such large effects. There, we are in the static range. There, it often almost looks as if the deep rolled one were worse. But that is, let's say, an artifact of the statistical evaluation. We can assume that it's actually identical. Due to the statistical evaluation, it sometimes looks as if the turned or non-strengthened curve is a bit steeper and accordingly has a higher static strength. But that's usually not true. No, it's just there. It's comparable in the area of fatigue strength. There, we fundamentally raise the range because we can slow down the crack growth. With that, I'm at the end of this video. I would like to thank you very much for your attention. Feel free to share this video with interested colleagues who would also like to know why they can use this process at all, or why they might have to use this deep rolling process, perhaps as well. Then you can just explain it. And exactly, feel free to share this video, feel free to like it on our social media channels so that we can tell as many people as possible about it. And if you have any questions, you are welcome to contact me or my colleagues here at ECOROLL AG.